we are going to see the basics of the transportation model, and then we'll be moving towards the numerical in the next lecture. We'll be starting with simple numericals in the next lecture, but for this the understanding is required regarding what actually is the transportation model, what are the assumptions that we are going to do, and how we are going to define a transportation model in the form of a numerical pattern, right? So let's understand transportation model, and then we'll be moving ahead with all these terminologies. So what is a transportation model? It deals with the transportation of a product available at several sources to a number of different destinations. So there can be a particular, no, there can be a company which is manufacturing like at four different places the same product, and no, there are number of destinations to which it has to send. So how this particular problem is to be solved, and how the what is the objective function for this particular problem, that also we are going to see. Now this is what I've told here, like firstly a very simple understanding of transportation model, that is no, it deals with the transportation of a product available at several sources to a number of different destinations. So no, particularly the word transportation comes into this under no explanation, but however the the name transportation model is misleading. It has various number of applications, hence we cannot say that it is only used for the transportation problem. However, in our syllabus we are only going to restrict ourselves with no, the transportation numericals, but it has various application. The model can be used for a variety of situations such as scheduling, production, investment, plant location, inventory control, employment scheduling, personnel assignment, product mix problems, and many other. Right. So there are various use of this transportation model, and the direct and the indirect application of this transportation model can be used in the various fields of management, right? So though the name is transportation model, it not no we no particular this model is not restricted with transportation only. It has various applications. So I've included this statement here, that the name transportation model is however misleading. Now let's see how when this particular model came into existence. Now this origin of this model dates back to 1941, right? So 1941, the mathematician called as F.L. Hitchcock presented a study entitled "The Distribution of a Product from Several Sources to Numerous Locations." Then the work on this particular model started. Many mathematicians got involved. In 1947, P.C. Koopmans presented the study of no, he presented his study titled as "Optimum Utilization of the Transportation Study," and these two mathematicians are are considered as the pioneer in this field of transportation model. And the research that they made, and that was a very basic research related with the transportation system only. But then various mathematicians came together. They understood what the previous researchers have how they have constructed this model. They understood the model, and they started to use that particular model in the various aspects as and as per their requirement, right? So they started modification of that particular thing. So in our case, for our syllabus, that is for our syllabus, we are going to deal with the transportation model involving number of shipping sources and number of destinations. So here, what we have for syllabus, including the variants, is we are going to consider a transportation model in which involves a number of shipping sources. Number of shipping sources, you can eliminate the word shipping. Shipping, that means shipping sources means that actually what I was trying to uh, mean here is the sources from which the transportation or the shipment will actually start. And no, I have used the word destination. That means that the shipment or this transported material will reach to a certain location. So that will be called as the destination. So we normally have we have number of sources and we have number of destination. We have a single product and we have to deliver it efficiently in this particular model, right? So now let's understand this particular in more detailed format. Now each shipping source will have a certain capacity, right? So the production at a particular source is not an infinite no, it isn't infinite. So there is a certain capacity of each source. For example, if I'm no if I'm manufacturing or no manufacturing a pre-stressed beam, right? So particularly I'll have a certain capacity depending upon the number of resources that I have. Resources in the case, the number of personnel working or the number of laborers working at my site, plus the capacity, plus the cement availability and the material availability, everything, plus the area availability. I have to consider everything, and depending upon that particular thing, every source will have a certain capacity. The capacity of a shipping source or a capacity of a capacity of a source is not infinite. Also, each destination will have a certain requirement. Even the destination won't be having an infinite demand, right? So if there is an infinite demand, there will be you'll have to have an infinite space and all those particular resources also you'll have to manage infinitely at the destination, with at destination point as well. So what we have is we have various number of shipping sources, we have various number of destinations, and for all this shipping, for if we consider the shipping sources, the capacity is finite, and for the destination as well, the capacity is finite, right? So what will happen again if I have to ship a particular product from one factory to a certain destination? It will again involve some cost, right? And again, particularly what will happen, a certain cost of shipping from a source to destination is also associated with that particular product. So here we have taken, we have tried to model this a realistic format. So that means that realistic format means that a source has a definite capacity, destination has a definite demand, and also from the transportation of one, the transportation of a product from the transportation of a product from a shipping location to a destination will acquire some cost. Now, what is the objective of this particular transportation problem? The objective of this transportation problem is to minimize the cost of transportation. So that is the no that is the case with this type of transportation model. So what is here? I'm repeating the objective. The objective is to minimize the cost of transportation while meeting the requirements of the destination, right? So we'll have to, not only destination, we'll have to meet the requirement of your requirement of your source as well as the destination. So we are going, the objective of this entire transportation model, please understand this and keep in mind, the objective is to minimize the cost of transportation while meeting the requirements of your while considering the constraints at your source end as well as the destination end. Now, the transportation problem may involve a movement of a product from a plant to a warehouse, from a warehouse to a wholesaler, from wholesaler to a retailer, and retailer to a customer. So now, particularly, the transportation model can be framed at this particular, in this particular format. So where you have a plant, right, which is a source, and you have a warehouse, which is what it is, a destination, right? So this is one type of problem that we have. Again, we may have a different problem in which your warehouse is acting as a source and your wholesalers are acting as a destination. Another type of problem in which your wholesalers are acting as a source and the retailers are acting as a the retailers are acting as the destination. And again, we may have a problem in which the retailers are acting as a source and the customers are acting as a destination, right? So this kind of numerical framework can be can be made Now, when I say that when I say it that we are going to deal with the movement of a product, so this particular product no can be anything. It can be a cement bag. It can be no. It can be a toothbrush. It can be the aggregates that we require from a crusher to the site. So this particular problem, we are going to solve it in the generalized manner, but just we can replace a product, and that particular can be a civil engineering oriented problem, or replacement of that product can be made as a mechanical engineering problem, electrical engineering problem. So what we are going to see the problem is is it in the generalized manner, but you according to your problems that you are facing, you can change the product, you can change the constraints, and all this will be a problem in which you can make it more realistic at your end, right? So the applications are many. Let's understand the assumptions that we are going to deal with the transportation model, right? So assumptions are very very important. We are every time when we are going to design any model, any mathematical model, we are going to try to make it we are going to try to make it maximum in a maximum manner a realistic model. But what may happen is that if we there can be certain complexities, and because of those complexities the model cannot be framed out. So all these complexities can be diluted, can be no, can be yeah can be diluted and in the form of the assumptions. So what we are going to do, or what we are going to see the assumptions in the transportation model are that will make the transportation model less complex, but maximum no, in a maximum way a realistic model. So the first assumption that we have is total quantity of the item available at different sources is equal to the total requirement at the different destination, right? So what we are going to know, particularly if I am having the availability of, let's say, I require no I require 100 of no say I require 1 lakh of cement bags. No, so the particularly my demand should match the no my demand should be matching the capacity of that particular factory as well. So the quantity of the total quantity of the item available at the different sources, no, that is equal to the total requirement. So what we are particularly telling here, that the product that we are going to deal with is not a scarce product, right? So if there is a scarce product, then there is a lot of complexity that are involved. This is not a scarce product. Here the product is available with with the particular factory as well, and the product is demanded at the demanded by the market as well. But the total quantity of the item that is available, so the total quantity available at the source is equal to the total requirement at the destination. So that is our first assumption. And when the total quantity of the item available at the different sources is equal to the quantity demanded by the destination, so such type of transportation model problems are called as the balanced transportation model, right? So here what we can say according to our first point is that demand no the supply is equal to demand. When the supply is equal to the demand, then it is called as the balanced transportation problem. If supply is not equal to the demand, so that particular problem is not a no that is unbalanced transportation problem, and it may require a different approach, right? So next assumption we have is item can be transported conveniently from all sources to that destination. So the product that I have, I can transport it conveniently from all sources to that particular destination, right? So this is very easy to understand, a very straightforward, right? So if it is not no if I'm not able to conveniently transport that particular product from a certain source to a certain destination, so I will have to eliminate the possibility of transporting that product only, right? So no, if I'm not able, there is no route that is available. So if there is no route, then the product won't be reaching from a source to destination. So that is the simple meaning with our second assumption. The third assumption that we know for this transportation model is that the unit transportation cost of the item from all the sources to destination is certainly and precisely known, right? So there can be four different sources, right? And there can be five different destinations. So the unit transportation cost from each source to each destination is precisely known, right? So this is no, then only we are going, no, then only we can find out the transportation cost, and then only we can minimize this no, the total transportation cost. So to know what is the total transportation cost and further optimization of the total transportation cost, we at a basic level require the unit transportation cost of that particular product from all the sources to all the destination, right? So this data is precisely known. That is the no that is the case with the transportation model, right? So now the transportation cost on a next assumption is the transportation cost on a given route is directly proportional to the number of units shipped on that route. Now this assumption is very important, and this assumption makes this entire numerical as a linear programming model, right? What they are saying that the transportation cost on a given route is directly proportional to the number of units shipped on that route. So if I'm shipping one unit, so particularly the cost will be, let's say, 1 rupee. If I'm shipping that particular 10 units, so the 10 units, for the 10 units the cost will be 10 rupees, right? So this is a linear relationship, and this particular assumption helps us to tell us that this problem is a linear, no, it is a linear programming model, or it is the LPP, right? Right. So the next thing what we have, the assumption, is the the objective itself of the transportation model. The objective is to minimize the total transportation cost for the organization as a whole, and not for the individual supply and the distribution center. So here what we have in the what we have in the prime focus is the is the organization, right? So what we are going to deal with is the we are going to minimize the total transportation cost for the organization. We are not going to deal with an individual destination or an individual distribution center. The prime focus is the total minimization of the total transportation cost for organization, and we are not going to keep in focus the individual supply centers or the individual destination or the individual distribution center in the focus, right? So I think that I had made my point regarding I made you understood regarding the transportation model, right? So now let's define this particular problem, right? The definition of the transportation model is very easy to understand, provided you keep your attention here. So I want everyone's attention here. So let's define the transportation problem. Suppose there are m sources, right? So we have given the name to number of the sources that are available are m, and the number of destinations that are available are n, right? So let ai be the number of supply units available at source I. So if there is a factory, let's say that there are three factories, one located in Pune, other located in Pimpri Chinchwad, and other located in Mumbai. So Pune factory has 20 units, PCMC, the Pimpri Chinchwad factory has 40 units, and the Mumbai factory has 50 units. So the value of AI, that is the number of supply units available at Pune, Pimpri Chinchwad, and Mumbai, are known to us, right? So the number of supply, the let AI be the number of supply units available at the source I, and where I is equal to 1, 2, 3 till m, right? So why m? Because the m are the number of the sources, and the sources will only have the supply units, right? Supply units availability will be there at the source itself. Nextly, we have the let bj be the number of units, no the be the number of the demand units required at the destinations, right? And the value of j will be from 1, it will be 1, 2, 3 till n. Why n? Because the the n is the number of the destinations. So for that particularly, there can be now, we have Pune, Pimpri Chinchwad, and Mumbai has a factories, and we have the warehouses of these factories located at, let's say, in Akurdi, or no, Akurdi in Pune, in Kasbapet, and particularly in Mumbai at any location, let's say Mulund, and one more warehouse of them located at Kalyan, right? So these are the four destinations, and the demand of each destination is known, right? And that has been represented by this BJ, right? So we had three factories and the four destination. Now let Cij represent the unit transportation cost for transporting the unit from source I to destination J, so that the total transportation cost is minimum. So now what I know the value of Cij. What is Cij? It is the unit cost of transportation of a product from the I factory to J destination, and it is known precisely. In assumption, we have already seen. So let's check out this particular, no, let's check out this with the example. So I have the factories in Pune, Pimpri Chinchwad, and Mumbai, and I have four warehouses at the different location. Let's say Kasbapet, here in Akurdi, then there is in Mulund and Kalyan. So the transportation cost, the unit transportation cost of a single product to be transported from Pune to Kasbapet, to Akurdi, to Mulund, and to Kalyan is known. Again, the unit transportation cost of a product from Akurdi to, sorry, from from a factory in Pimpri Chinchwad to the destinations at Akurdi, Kasbapet, Kalyan, and Mulund is known, right? Another case, my third factory is located in Mumbai. The unit transportation cost of the factory, the unit transportation cost of a product located from factory towards the warehouses in Kasbapet, Akurdi, Mulund, and Kalyan is known, right? So the unit transportation cost from each factory towards each warehouse is known, and that is represented by Cij, right? So in addition, the supply limits at the sources and the demand requirements at the destination must also be known. So I should know what is the capacity of the production of factory at Pune, Mumbai, and the Pune, Mumbai, and Pimpri Chinchwad. And I should also know what is the demand requirements of the destination. So I should know what are the what are the demands of these warehouses located at Kasbapet, Akurdi, Mulund, and Kalyan, right? So now let's particularly understand. Let's stop at this particular juncture for this lecture, because it is 10:38, and I don't want to extend this. Okay, we started at 10:10, no? So we can continue till 10:50, right? Okay, so let's continue. Sorry. Nextly, if Xij, that is, Xij are the number of units, right? So Xij is the number of units shipped from source I to destination J. So for example, I'm shipping from a warehouse at, I'm shipping from a factory at Pune to a warehouse at Akurdi. So how many number of units I'm shipping is represented by Xij, and Xij should be always greater than or equal to 0, right? So your Xij can't be negative. It should be either a positive or it should be 0, right? Then the equivalent linear programming model can be represented in this particular fashion. Let's understand how the linear programming model will be represented. So I made my point, I guess. I'll be repeating. There are M sources, N destinations. AI is the number of supply units from supply units available at the factories, and BJ is the number of demand units for the destinations. Cij is the unit transportation cost from I factory to J destination, and Xij is the number of units shipped from I factory to J destination. Now let's represent this particular in the form of numerical. What we have to do is we have to find this value of Xij. Everything other than Xij is known to us. We have to decide how many units are to be shipped from this particular factory to that particular destination, so that the the demand also get fulfilled and all the constraints get fulfilled, and we have the less minimization or the minimum transportation cost. So what we have to find out is we have to find out xij, where I is from I to 1 to m and j is from 1 to n. In order to minimize, we have to minimize the transportation cost, the total transportation cost. So we know what is CIJ, that is unit transportation cost, and we know how many units we are going to supply. So the multiplication of these two will be what it will be the transportation cost, right? So right, I think that you are understanding. If not understood, I'm repeating this. CIJ is the cost, the unit cost of that particular unit, and xij is the number of units. So what, let's say that particularly if I'm transporting the five products from Pune factory to Kasbapet warehouses, and the unit transportation cost is 10 rupees, right? So I have to transport five products, and the unit transportation cost is 10 rupees. So my CIJ value is how much? My CIJ value is 10 rupees, and my XIJ value is five numbers. So my total transportation cost will be 10 into 5 is equal to 50. And this particular transportation cost is for which route? It is for the route of your, from Pune to Kasbapet only. So what I have to do is I'll have to minimize this particular Z, which is the total transportation cost. And how I will be minimizing this particular Z? I'll have to take into consideration the total transportation cost, and hence this particular summation sign has been used, right? So I'll have to, this particular sign is summation is for your Cij, Xij directly. So here this particular I is from 1 to m and your j is from 1 to n. So the summation of the total transportation cost will be what it should be minimum, right? And what are the constraints with us? Subject to. Subject to, that means that we have constraints. What we have constraints is the AI. What is AI? AI is the number of supply units available at the factory. This is the very important constraint. And what is the next constraint that we have is the BJ. What is BJ? BJ is the, no, it is the demand of that particular demands of this demand of the destination. So I have to, what are my constraints? I have to take into consideration the source, the number of units available at the sources, plus I'll have to take into the consideration the number of units that are required by each destination. So this happens to be my what? This happens to be my what? Constraint, right? So this is the linear programming model in which you have an objective of minimization of, yeah, okay, you have an objective of minimization of the total transportation cost, subject to what? Subject to the total supply available and subject to the total demand of the destination. Here particularly I'm writing xij now. No, if you understand this, it is very easy. So what is your AI? What is your total supply? Total supply is the, no, particular, your total supply should match the total number of units. And what are the total number of units? It is xij, where your I is from 1 to m and j is from 1 to n. So my xij should be equal to the total supply available. What is xij? Xij is my number of units shipped from a source to a destination. So my summation of xij, or particularly the total supply here, the total supply here should be equal to the, no, sorry, the total number of units supplied should be equal to the total number of units available at the factory. Similarly here, the total number of units supplied is equal to the number of units demanded by the destination. So here, if you understand this, it is very easy to understand a transportation problem. I'm repeating this. The total supply of units that I have made is equal to the total number of units available at the factory, and the total the total number of units that I have supplied is equal to the total demand by the destination. Now, if you see this particularly from this, you will be, if I cancel this xij, xij, I can cancel this xij, xij because it is representing the same quantity. That is the total number of units supplied. So if I'm representing the same thing, I can cancel this. And particularly what I can say, but the number of units available for the supplied resources, no, is equal to the number of the units demanded by the destination. So what I can write is that I can eliminate these two particular xij's, and what I can write is the summation of all this AI, that is the total supply, is equal to the total demand. And this particularly we have already seen. I've just represented it in the form of a model, and that particularly is nothing but this. uh, it is the numerical is called as the balanced transportation model, where supply is equal to demand. So what I have done in this, in this particular stretch here, is I have defined the objective function and the constraints, right? Here was my objective function, which was minimization of the total transportation cost, and here I have this as the constraints. But we'll have to understand this: the total supplied units are same only. That means that my total supply is equal to the total demand, which is represented here, and it is also given here, where supply is equal to demand, and hence it is called as the balanced transportation problem, right? So now this particular relationship, that is the total demand is equal to the total supply, is necessary as well as the sufficient condition for the transportation model, right? So how this can be, how the can be represented in the graphical format with the help of the matrix. So this is the matrix representation. On this particular side, that is the extreme left, all the sources are represented. Here you can see the source number 1, 2, 3, dash 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 dash, and the last source is M, right? So all these sources are represented here, and all the destinations are represented here. So these all are your destinations: 1, 2, 3, and lastly you have N, right? So this is my first factory, right? This is my first source. That means that it is my first factory. The supply available at this particular factory is represented here. Here you can see I've written supply. Okay, it is equal to A1. Similarly, factory number 2, the supply for no the supply available at factory number 2 is given here, that is A2. Supply available at factory number 3 is given here. Supply available at factory number M is given here, right? Similarly, the demand is also represented. The demand for destination 1 is given here, that is B1. The demand for destination 2 is given here, B2. The demand for destination 3 is given here, B3. And the demand for your last destination, N, is given here, Bn. So what is now here C11? C11 is the transportation cost of, no, it is the unit transportation cost of product supplied from one factory number 1, to the destination number 1. C12 is the unit transportation cost of the product supplied from factory number 1 to the destination 2. Similarly, the value of C13 is nothing but the unit transportation cost of a product supplied from factory number 1 to the destination number 3. Similarly, you can see here also, if I have to consider C3N. So what is C3N? It is the unit transportation cost of a product supplied from factory number 3 to the destination number N, right? Similarly, I have CM2. So what is the meaning of CM2? CM2 is the unit transportation cost of a product supplied from M factory to destination number 2, right? So I think that you have understood. It is this particular value of C11 is to be written at extreme top of this particular cell. Everywhere you will be seeing that I've written C1s, all the C values are written at the top. Now what is X11? X11 is the number of units supplied from factory number 1 to destination number 1, right? So next, X12 is the number of units supplied from factory number 1 to the destination number 2. Similarly, what is C33? C33 is the, sorry, X33. What is X33? X33 is the number of units supplied from the factory number 3 to destination number 3, right? So all x3 no all the x values are to be written at the bottom of this particular cell. So this is how this particular is represented. So here all you have is the supply. Addition of all these values is equal to the total supply. Here you have demand. The addition of all this demand is equal to total demand. So now if you see that I have transported how many units from factory number 1, x11 plus x12 plus x13 plus x1j plus x1n. So addition of all these units, that is x11 plus x12 plus x13 plus x1j plus x1m, should be equal to A1, because that is the total demand for that, that is the total supply for that particular factory. So here you will be seeing that the x11 plus x12 plus x13 plus x1j plus x1n should be equal to A1, and this A1 value is already known to us. What we are interested in, we are interested in finding out what is x11, what is x1, all the x values we are going to find out. We know all here what is known, all these values are known, all these values are known, and all these c values are also known. What we are going to we are interested in finding out this x. So this values of x we are going to find, and those values of x should be such that this x11 plus x12 plus x13 plus x1j plus x1n should be equal to A1. This is my constraint, what we have earlier defined. Similarly, all these values of x in your row number 2 should be equal to A2. Similarly, all the summation of all the values of x in row number 3 should be equal to A3, and likewise. Similarly, so I think that the row wise you have you have understood. Similarly, the addition of x11 plus x21 plus x31 plus x1 xi1 plus x1m1 should be equal to B1. So addition of all this should be equal to, so because we are dealing with that particular first warehouse, so where first warehouse will have a demand of B1. So particularly we are going to find out all these values in such a manner that my A1, this particular, the condition of a row as well as the condition of the column will get satisfied. I have to satisfy the condition for all the columns and all the rows. So this is a very interesting numerical. I think